So he did his undergrad at UT Houston, PhD in scripts. I was getting a master's degree in there.
It's okay, I tried to skip it too.
He's got tons of awards, including the Presidential Early Career Award, which is basically the highest possible honor a young scientist can get. It means first you have to get nominated by your particular federal department, and then it goes to the White House, the President's office, and from the President.
So I got to shake hands with Obama.
Yeah, okay, so that's how cool he is, how lucky we are to have somebody with us today. So like, he's shaking Obama's hand, and so if you shake his hand, it's kind of like crushing his present. Practices.
Who is my left hand though, so you got to shake left hand.
So extremely, extremely up there. But that's not actually the only reason I asked him to come today. So I knew he was extremely successful and does great science, but he also has a real talent for connecting with people and interested in talking to people like you guys. So we invited him because we thought like somebody who could talk to you guys and get you excited about science and the questions behind it. So I'll let him take over because he's the expert.
Thank you very much. Okay, so first off, I talked to a few of you. How many people are biology majors? Yeah, that's what I was getting a sense of the numbers. That's fantastic. That's great. I don't know any biology, but I'm mostly going to talk about the physical climate. But if you have questions about the biology or the impact of this stuff on the marine ecosystems or whatever, ask me at the end, and I'll muddle through, and I'll tell you when I'm lost and I don't know what I'm talking about. So, okay, are you guys ready? You guys ready? Come on. Yeah, there we go. Yes, thank you, thank you. So what I'm going to talk to you about, you can, I think, yeah, hit the first slide. There we go. What I'm going to talk to you about really is the role of the oceans in global warming and climate change. And the oceans wind up being incredibly important in this problem. And if you think about it for a minute, you can actually figure out why. This is not that surprising a picture anymore. Everybody has Google Earth, and you can pop this up on your computer, and you know that if you just rotated the Earth a little bit this way, almost the only thing you would see in this picture is the Pacific Ocean. The Pacific Ocean is 1/3 of the planet, and 2/3 of the planet is covered in water. So you can imagine that if climate change is happening, and it's something that's happening to our entire planet, then the oceans are going to play a huge, important role in that process. And so what I'm going to talk about, for the most part, is how that happens and what that means and why you should all be thinking about the oceans in terms of global warming and climate change. Okay. All right, so I'd like to start off with a little bit of humor and jokes. So feel free to laugh whenever this happens. So a lot of people, give me a hard time about global warming and climate change and things like that. You hear a lot about this in the news. And one thing you have to remember when you're talking about this subject, and I think scientists, we often forget this, is that this is now not just our problem. It's not just a science problem. It is actually a societal problem. And that means that if we're going to look for solutions to it, we have to be willing to talk to other people that aren't necessarily scientists. So this is a place where science and policy and a whole lot of other things are actually intersecting right now today. And it's one of the reasons why it's interesting, but it's also one of the reasons why it's so full of conflict and anxiety for so many people. All right, so here we go. Global warming is, what do we mean when we say global warming? We actually have a very specific meaning when we say global warming. We have a specific thing in mind. What we're talking about is the warming of the average temperature of the planet over the last 100 years. So in the last 100 years, the average temperature of the whole planet has increased by almost 2 degrees Fahrenheit, about a little around 1 degree C, something like that. And this doesn't seem like a lot, right? I mean, when it gets dark, it goes down many degrees in temperature, and when the sun comes up, it goes up many degrees in temperature. But you have to remember that this is something that's happening to the entire planet. So this is an average over every sort of square inch of the surface of the Earth. And to the best of our ability to actually measure that number, the average over the entire surface of the Earth, this is what it looks like. And you have to keep in mind also that when we're talking about global warming, we're talking about something that's taken 100 years to begin to play out. So even though it might be hot today and cold tomorrow, we might have a hot year this year and a cold year that year, what we're talking about is this slow rise in the temperature of the planet over the last 100 years. So there's a lot of things that global warming is, but there are a lot of things that global warming is not. And you have to be able to distinguish between the weather, which is the things that come and go, and the short-term changes like day to night, and like stormy to clear skies, things that happen over a few weeks. The climate is what happens over the long term and over kind of the large scale. So keep that in mind. Okay, so next slide. In the last 10,000 years, this is very important. In the last 10,000 years, we've actually had a very stable climate. So during this time, about 20,000 years ago, we were in the middle of an ice age. We were at the peak of what's called a glacial maximum. So that means that there was a giant ice sheet covering a lot of North America and Canada. Places like Chicago were under miles of ice. And the entire planet was 5 degrees C colder in average over the whole planet than it is today. So it was a massively different place to live. And not only that, actually, if you look carefully in the record, it seemed to change very fast. So it would get really warm and really cold. And it was actually impossible for people to begin to build a civilization, for people to begin farming, to begin to have states and technology, develop technology, and build highways and make cell phones and eventually iPads. That didn't happen until really the climate began to stabilize. And this is an important concept because for the last 10,000 years, the climate, we've had some big swings in the temperature of the planet. We had the medieval warm period, and you'll hear people talk about this as the time when Vikings began to inhabit Greenland, and the little ice age when they were basically all driven out by the cold, and the Thames River froze very famously during this period. So there were ups and downs, and these were big things. They actually had big impacts on the civilizations that experienced them. But look at the difference between the changes here and the end of the last ice age. So this was a massive shift, and it really had a fundamental impact on how people were able to sort of interact and live on the Earth. And we really weren't able to develop modern civilization until we were in this sweet spot. So the question is, what's going to happen now? All the predictions for the future, the next 100 years, in terms of how warm it's going to get, pretty much all the predictions are outside this comfortable window that we've had for 10,000 years. So think about that for a second. That means that the civilization that we built was built during a climate that we are no longer going to have. That climate will be gone. We will have a new climate. We don't quite know how warm it's going to be or how exactly it's going to change, but the climate that we're going to get in the next 100 years is going to be different than anything we've experienced for the last 10,000. Okay, next slide. So, question. What causes global warming? Go ahead, this is the part where you can just yell it out. It's all right.
Cars.
Everyone's awake. What is it?
Cars.
Cars, what else?
Greenhouse gases.
Greenhouse gases. I was actually looking for Democrats. This is one of my favorite pictures of I call him Al. Al is great. If you haven't seen his movie, An Inconvenient Truth, you should see it. Climate scientists, who are very gung-ho will tell you, oh, we made this mistake and that mistake and blah, blah, blah. And some of the things that he says, some of the little tidbits and facts that he says in the movie, we found out new stuff since then, and they're modified and changed. But the basic picture of what he said in the movie is right. Human beings are warming up the planet. Now, it's not really Al. You can't blame Al. So this is not real. But go on to the next slide. This is what really causes global warming. The main driver for our changing the climate in the past 100 years and in the next 100 years is the emission of carbon dioxide into the atmosphere by the burning of fossil fuels. So what do I mean by that? I mean, what we're doing is almost all the energy that we have, the energy we use to drive our cars, to power our lights, the vast vast majority of it comes from digging up fossil fuels, things like oil and coal, and burning them. So when we do that, we're taking carbon that was stored in the ground, putting it in our gas tank, burning it. The carbon gets broken up and attached to oxygen, so you get CO2, and this remains in the atmosphere. So this carbon that we put into the atmosphere actually will remain there for as long as 1,000 years. Some part of it that we put there every ton will remain in the atmosphere for 1,000 years. And most of it will remain there for hundreds of years. So when we're doing this, we're actually having an incredibly huge impact on what makes up our atmosphere. Now, if you look on the right side here, this is parts per million. So you might say, oh, well, that's a really small number. How could that little carbon dioxide have any impact on the planet? And the reason is because carbon dioxide has this special property with how it interacts with light. And so we're back. And we're back. So this graph, though, shows the carbon dioxide in the atmosphere for the last 500,000 years, or nearly 500,000 years. And what you see is these lows and highs. These are the cycle of the ice ages. So you have warm periods like this. This is called the last interglacial, so between big glaciers. And so this was a warm period, and then we had a cool an ice age, and the last glacial maximum was here. It's about 20,000 years ago. And then we warmed up, and we warmed up into this warm, stable climate. The little 10,000-year part is too short to see here. It's just right there in the end. And then for the last, actually it's about here, and then for the last 100, 200 years, we've been driving the carbon in the atmosphere, the carbon content in the atmosphere, very high. It's almost to 400 parts per million. In the next decade or so, it will be at 400 parts per million. And that's higher than it's been at any time in the last 500,000 years. So this is a really profound change in terms of the carbon concentration in the atmosphere. And you really can't expect, so this carbon, furthermore, this carbon actually is has a certain isotopic ratio that allows us to actually trace it to the fossil fuels that it came from. So not only do we know that we burned this much carbon and it's gone into the atmosphere, we can actually see the markers on that carbon and actually tell where it came from. And we can see that all this is fossil fuel burning. So we know that humans did this. There's no debate. Not even the deepest climate denier would deny that this was caused by people. Okay, next slide. So how do we know that it goes back, this was 500,000 years of data, and obviously there weren't scientists back then. So one of the ways we know about what happened 500,000 years ago is by looking in places like ice cores. So whenever snow falls in a place where it's cold, and it's not warm enough to melt all the snow through the summer cycle, then the snow accumulates, maybe some of it melts. Then the next year some more accumulates, and then it melts, and then some more accumulates, and it melts. And you get these annual layers, and they actually trap part of the atmosphere inside those little layers. And by drilling down through them, you can actually get a record back hundreds of thousands of years in some places. So with this information, we can not only tell what was in the atmosphere, what the composition of the atmosphere was, what the CO2 was like, how much CO2 was in it. We can also tell what the temperature was separately because of different ways of counting what's inside.
Can I ask a really basic, silly question?
Please.
When you talk about it being trapped in the ice, is it literally, let me be simple, the snow comes down and traps air with it, or is it in the snow?
It's just the snow flakes falling and kind of compressing, making little cavities that hold.
So it's air in it.
It's like little bubbles, right?
Okay.
Right, they get trapped. They're not exact. People, the folks that do this don't like to call them bubbles exactly, but it's the snow gets compressed and it holds some of it. And part of that also, I think, has to do with the melt layers. The exact physics of what's going on in the surface layers is kind of complicated. You get a little bit of melt and everything kind of runs together. And so the records aren't always, you can count back years by looking at the layers, but sometimes the gases or whatever spread out, and so it's a little more complicated. But basically it's just, the snow falls and it traps part of the atmosphere. By studying those little bubbles, you can figure out what's going on 500,000 years ago. Okay, so this is a slide that every global warming talk has, and you've probably already seen it before. But basically, the way global warming works is that all of the important energy we get in our climate system comes from the sun. And that energy is basically in the form of visible light. And visible light has the property that it more or less goes right through the atmosphere. So this energy that comes from the sun is, the atmosphere is transparent relative to that energy. So the energy actually goes right through the atmosphere. It bounces off some clouds, maybe a little bit, but most of it goes right through, and it warms the surface of the Earth. Now, the warm surface of the Earth emits energy back into space, just from the basic laws of physics. Anything that has a temperature above absolute zero, even all of you, are emitting radiation. And so this radiation is carrying energy away from the surface back up towards the atmosphere. But there's a catch, because this was visible light, which means that it was short wavelength, special kind of radiation, and it went right through the atmosphere. This is a long wavelength radiation, so it's kind of like a different flavor of energy that's coming off the Earth. And that energy actually interacts with the CO2 molecules. So the CO2 molecules and other things in the atmosphere absorb that energy, and then they re-emit it and absorb it and re-emit it. Eventually, some of it makes it out of the atmosphere. But some of it gets trapped. And when you add more CO2 to the atmosphere, you're increasing the amount that gets trapped, that gets sent back and bounces back between the surface and the atmosphere, and etc. So you're reducing, when you add CO2 to the atmosphere, you reduce the amount of energy that escapes back out into space. Now, the question is, where does that energy go? Anybody have a guess? You don't get to guess. Yes?
Into the oceans?
Exactly, it goes into the oceans. Next slide. Over 90%, in fact, of the extra heat that gets trapped by these greenhouse gases winds up going into the oceans. So this is kind of an amazing fact, right? Because I showed you that plot at the beginning of the temperature rising, and that's the temperature really of the atmosphere. So we live in the atmosphere, we care about the atmosphere. The atmosphere is where we really see the global warming happening, right? But actually, most of the global warming is happening in the oceans. 93.5% or more. So the oceans are really, in a way, the most fundamental marker for how we're changing the climate. If you really want to see where global warming is, it's happening in the oceans. The atmosphere, that warming curve, is only 2.3% of this energy goes towards warming the atmosphere. Okay, so the question is, why does this happen? Now, there's a great little experiment that will demonstrate why this happens. If you were to take a balloon filled with air and hold a flame to it, sorry, there's a few in this one. What happens? It pops, right? Now, if you're to hold a flame to a balloon filled with water, what happens? Any ideas? Well, there's only one way to find out, right? I need a volunteer. Who wants to come up and... Yes, in the back. All right. Fabulous. Okay, so you're not afraid of loud noises, are you?
We'll see.
I guess we'll find out, yes. All right. What's your name?
Carly.
Carly. Very nice to meet you. All right, here we go. So what we're going to do is you're going to hold this balloon. Okay, I'll hold the balloon. You're going to hold this balloon, and we're going to go over here. And maybe I'll just turn the lights up for a second. Is it this switch? Yeah. Fabulous. All right, so is everybody ready? Is Carly ready? I don't think Carly is ready. Here we go. Carly's ready. All right, you guys ready? I don't think you're ready. I don't think.
Check my eyes.
brave volunteer? Who's bold and nobody's bold and brave? Come on. A volunteer. From this side. I didn't get to talk to you guys. All right, somebody get up. Yes, yes. All right, yes, yes. Oh! I used the force on that one. Good job. Stefan, very nice to meet you. Okay, so here's what we're going to do this time. I just happen to have a water balloon in my car. And now, what's going to happen is the water balloon is not going to pop. And the reason it's not going to pop is because water is so good at absorbing heat that the skin of the balloon, you don't believe me at all, do you? The skin of the balloon doesn't have time to melt, and so the balloon won't pop, right? Are you ready? Okay, so come out here in the middle so that we don't hit the projector. And hold it up real high. Okay, you got to give me a little space between your fingers so I don't burn you. Okay. This never fails. The balloon, I promise, will not pop. I'm a professional. I know exactly what I'm doing. It's a new jacket. I don't want to get it. Okay, here we go. All right, okay. You guys ready? Oh, you're going to need some more space between your fingers. All right. It's a heavy balloon, isn't it? Okay, you ready? Okay, why don't you spin around this way? No, you spin. There you go. Everybody see that? You getting tired?
A little bit.
So how long will we stand here before Stefan loses his grip and we all get wet? That's the real question, right? Okay, thank you. So is the balloon warm? No, it's almost exactly the same thing. You can't tell the difference at all. Lovely. Thank you very much, Stefan. All right, another round of applause. Okay, so what happened? Well, what happened was, you can't see the projector anymore. What happened was that the heat, it's just like I said, the water is so good at absorbing heat that it really doesn't give the balloon time to melt, and so the integrity of the balloon remains. And you can actually stand there. I have a friend who did this with a Bunsen burner for 20 minutes, and the balloon never popped. Although a blowtorch will do it. You're going to try it at home, a blowtorch will pop the balloon. But this is important because the oceans, if you add up their ability to sort of hold heat, it's 1,000 times bigger than the capacity of the atmosphere. So if you want to change the temperature of the entire ocean by 1 degree, or you want to change the temperature of the entire atmosphere by 1 degree, it takes 1,000 times more heat to change the ocean temperature than it does the atmosphere. So this is really the main reason why all the heat goes into the ocean. Now, not the entire ocean is in contact with the atmosphere at any given time. It warms slowly, kind of from top to bottom. But nevertheless, this remains true, and it remains the reason why the oceans are one of the most important factors for how global warming proceeds, how quickly it proceeds, and what happens as it does. Okay. So we're going to go back to our little diagram again. Remember, we have the sun, we have energy coming in. This is the sunlight, and then the energy going out is what we call infrared or long-wave radiation for the most part. Some of it is reflected, but if these two things were equal, then the temperature of the Earth would remain the same, right? Just like it did for that 10,000 years, for the most part, of stable climate that we had, which we call the Holocene. So during the Holocene, these two things were equal. Now, hit the button once. When we began to add greenhouse gases to the atmosphere, what we essentially did is we reduced this outgoing radiation. So we're keeping more of the energy on the planet. And if you keep more energy, if you keep more heat on the planet, it has to heat up, right? So if it heats up, then eventually, one more time, eventually the warm Earth will begin to radiate more energy back out into space. And eventually, as it warms up and it radiates more energy out into space, we will achieve a new balance. So in the long run, with a set amount of CO2 in the atmosphere, we'll eventually reach a new equilibrium, but the penalty is a warmer world. And it would have to stay that temperature unless we remove the carbon dioxide from the atmosphere. So as long as we have a certain concentration of carbon dioxide in the atmosphere, then we have to have a certain temperature of the Earth in order to maintain this balance. Does that make sense? More or less? Maybe it would with coffee. Okay, so one more. The key, though, is remember, to heat up the planet, 90% of the heat is going into the oceans. So if you're going to put heat on the planet, if you're going to heat up the planet, you really are heating up the oceans. And to heat the oceans from top to bottom takes about 1,000 years. So whatever we do, if we put carbon dioxide in the atmosphere, and it's going to stay for a long time, then the oceans are going to continue to adjust to the presence of that carbon dioxide for 1,000 years. So whatever we're doing to the atmosphere today, those changes are going to be with us for a very, very long time. Now, most of the warming happens, like 90% of the warming happens faster than this. But some things really will continue to happen for 1,000 years, like the rising of the oceans. Just the heat going into the water makes it expand. And that expansion of the oceans will continue for 1,000 years. So the thing you have to realize is that when we put carbon dioxide in the atmosphere, it's sort of like taking a genie out of a bottle. It's very hard to reverse this process. We put the carbon in the atmosphere, and actually half the carbon that we put in the atmosphere winds up also going into the oceans. So if we wanted to get that carbon back, we could take carbon out of the atmosphere, and then the ocean would put some more back in. So the same thing is true with the heat. If we're trying to cool down the planet, we can't just cool off the atmosphere because the ocean will just keep releasing heat back into it. So the oceans provide this inertia for the climate system. Once we've changed it, once we've moved the goalpost, and once we've added a lot of heat and a lot of carbon to the oceans, it's really hard to reverse that process. And this is very important because that tells you that climate change, what we do to the atmosphere, is really, for the most part, it's irreversible, what we've done. That's not entirely true. There are ways to begin to draw down the carbon, but it would take a very long time, and it's a very slow process. So these are things that we're committing to. We're committing to a new future. So the question is not whether we're going to undo global warming. It's where are we going to land? Just how much are we going to allow? How far are we going to go down the rabbit hole? Okay. So, is global warming real? I'm going to spend a few minutes on this. So next slide. A few people would tell you that global warming is not real, even today. This cartoon's a little bit old, but it's still true. My friend here from the Institute of Deep Denial and Corporate Smile would say, we definitely know two things to be true. First, the Earth is not warming, and second, it's flat. But you don't have to be a member of the Flat Earth Club to believe that global warming is not real. My buddy here, Rush Limbaugh, actually doesn't think global warming is real. At least he says he doesn't think global warming is real. And actually, I have a little story. Not too long ago, or it's been a few years now, actually, I wrote a paper. I did some research, and we calculated that the oceans had actually cooled down a little bit. And this was kind of big news because, you know, we're adding carbon dioxide to the atmosphere. How could the oceans cool off? And a lot of people actually, you know, were sort of, a lot of scientists were skeptical about it. And of course, the blogosphere and the climate deniers kind of lit up with activity. Oh, climate science is all a scam, and, you know, global warming's a lie. And Rush Limbaugh actually used our paper in a nationwide radio broadcast to say that global warming was, that actually climate scientists didn't know anything about global warming, that this cooling was just a complete surprise, and it was just proof that we have no idea what we're doing. And he had a great quote. He said, "To overturn the world economy based on the musings of a few idiot leftist scientists is just stupid, and that's what global warming is all about." Now, it was Valentine's Day, 2007, and my wife and I were just about to go out to dinner, and I was on the computer like I always am, and I made a sort of startling discovery. And I looked up and I said, you know, I think this ocean cooling thing might be wrong. And my wife said, let's go to dinner. And it turned out that ocean cooling was wrong. small group of floats, a small group of instruments that measure the ocean temperature, were malfunctioning, and they were reading temperatures that were just impossibly cold. And if you threw those bad readings out, if you fixed a few other problems, then ocean cooling disappeared completely. So the question is, what did I do? So what did I do? I actually published a paper about it. We highlighted our mistake. We said, this was wrong, and here's why. And the reason we did this is because that's a fundamental part of how science works. Not every science paper is true, and scientists are people, just like you guys. I think you're mostly people. And we make mistakes. But the idea is that the process itself and the scrutiny that we continue to apply to our observations and to our results eventually leads us down the right path to something correct. Now, the story had a happy ending. My wife eventually got me a brand new set of business cards. You can hit the button. And the job title on them is Idiot Leftist Scientist. So if any of you want an Idiot Leftist Scientist business card at the end, I'll be happy to give you one. But the point here is that, of course, Rush didn't have me back on his show to talk about the correction, right? And this is sort of a thing that I think is important to realize, is that there's sort of a fundamental difference between the way science works, where we scrutinize what we're doing and we look carefully at our results, and when we find a mistake, we tell you. And the media and the people who talk about climate science and the pundits and the folks like Rush Limbaugh, they don't necessarily do that. And so if you're not really paying attention, if you're not looking at the science and looking at the data and looking at the observations, it's easy to get misled by my buddy Rush. Okay. So, how do we know sea level rise is real? Next slide. I'm an oceanographer, so one of my favorite places, and I just told you that 90% of the heat from global warming is going into the oceans. So what's the best place to look for global climate change? In the oceans, right? And one of the best indicators for how our climate is changing over time, in my opinion, is global sea level change. Because you can't change the height of the oceans all around the world. Remember, it's 2/3 of the planet. You can't change the ocean volume without a really major shift in the climate. Now, remember, 20,000 years ago, we had a giant ice sheet all over North America. So North America is covered with this huge volume of ice. Now, ice is frozen water. Where did the water come from? Go ahead, Yelena.
The ocean.
Exactly. The water came from the oceans. So if the water wasn't in the oceans, then sea level was lower at the time, right? So in fact, we have really good observations that show 20,000 years ago, sea level was 120 or 130 meters lower than it is right now today. And as we warmed up out of that cold period and into this warm period, the oceans, the ice melted and the water ran back into the ocean and sea level rose. And it rose at a very fast rate. It rose at a centimeter or more per year, which is really huge. And for thousands of years it did this, and then around 5, 6, 7,000 years ago, global sea level rise basically stopped. We got into this, remember, we were in the 10,000 years of the Holocene, the very stable, warm climate, and we had a very stable sea level. And in fact, the last 3,000 or 4,000 years of sea level is less than 1/4 of a millimeter per year. Probably it's, for the last 2,000 years, it's almost perfectly stable. But if we look at tide gauge records that go back 100 years, then we can see a very clear signal. We see the beginning of global warming in the early 1900s, and this rise in global sea level. And the rise in global sea level for the last 100 years is 2 millimeters per year. So it's almost a factor of 10 bigger than any time in the last several thousand years. And in fact, we actually have really good records now that go back an entire 2,000 years, and we can tell, without a doubt, that the most recent 100 years are the fastest rate of sea level rise than any time in the last 2,000. So sea level was stable for 2,000 years, and now it's rising at 2 millimeters per year. And in fact, as you'll see in a minute, it's rising even faster than that now. So yes?
What's roughly the portion of the rise that's due to melting and more water versus expansion?
That's a great question. How much is just the thermal expansion of the ocean? Just like mercury in a thermometer, water expands when it gets warm. And part of global sea level rise is due to that. Today, it's about a third. In this period, it's about a third. At times where you have these huge changes like this, it's way smaller than that. Really, if you're going to have a huge change of many, many meters of sea level, it's going to be because of the ice sheets. And looking out into the future, the ice sheets are going to become more and more important in the next 100 years as they begin to react to the warming climate. That's a great question. Okay, so if we look carefully at the sea level record for the last 150 years, or 130 years, we see actually that sea level's gone up by about 8 inches, or 20 centimeters, in the last 100 years. Now, if you're standing on the beach and you're watching the waves roll in, that doesn't seem like a very big number. But you have to remember, this is the global average, and 2/3 of the planet are covered by water. And that means it takes something like, this means something like 16,000 cubic miles of extra water in the oceans. So it's really a massive change. And it's really something that could only have happened with a planetary change in the climate, something that really involves the entire Earth. And it's something that hasn't happened in the last several thousand years. So the only conclusion we can really reach, the only logical conclusion, is this is the direct cause of human-induced global warming. And in a way, it's one of the most profound ones we have. If you remember that line I showed you at the beginning that goes back to a similar amount of time, there are all these bumps and wiggles and periods of faster warming and colder warming and ups and downs. But actually, the sea level curve is very smooth. It's very clear. Because the ocean sort of adds up all of these effects together. It adds together the warming and the expansion. It adds together the sea level rise from the melting glaciers and ice sheets. It's all these things added together, so it's actually a very smooth curve. You'll hit the button once. You'll also see that it's not really a straight line. So the real number for the rate in the last 130 years is 1.8 millimeters per year, about 2 millimeters per year. But if you hit the button 3 times, you'll see that, in fact, if you divide this record up, now I haven't been careful about the way I've done this, but roughly speaking, 100 years ago, sea level rise was more like 1 millimeter per year. 50 years ago, it was more like 2, and now it's more like 3. So there's an acceleration as well. The rate of rise is increasing. And every reasonable projection into the next 100 years says that it's going to continue to accelerate. So our rate of rise of 3 millimeters per year today is going to get bigger. 16,000 cubic miles. Now, I work at the Jet Propulsion Laboratory, which is a NASA lab, and people often ask me, so you're an oceanographer, why are you working for NASA? And if you remember back to the very beginning of the talk, the very first slide, the oceans are 2/3 of the planet. And if you really want to have a good idea about what's going on in the oceans, almost the only way to see the whole picture is from space. And so we have all these really great instruments. These are Jason satellites, and they actually measure the height of the ocean from 800 miles in space with an accuracy of 1 inch. And they do this all around the planet once every 10 days. If you average all those 1-inch accuracy observations together, you can get a really incredibly great picture of how sea level rise is happening. And it looks like this. So this is the rise in the ocean. So I remember we were talking earlier about the changeover in the satellites. The very first one of these was called Topex Poseidon. It was launched in the early 90s, and it lasted all the way until the middle of the 2000s. And then Jason 1 followed it, and Jason 2 followed it. But what's amazing here is you get this really clear picture. The biggest thing, so there's ups and downs. This seasonal cycle every year, sea level goes up, and then it goes back down roughly a centimeter. This is actually because of the exchange of water between the oceans and the land. Every year, a huge amount of water is evaporated out of the ocean, it rains down over land, and it takes a while to get back to the oceans. So you can actually see this effect of the exchange of water between the oceans and between the land in the satellite data. It's that accurate. But what's amazing to me is that we have 20 years of this record, and the most striking thing, the biggest, most important thing in this record is what? The trend, right? The 5.5 centimeters of sea level rise. It's the clearest, easiest to see signal in this record. So, in a lot of ways, I think this satellite record is one of the most profound pieces of information we have about how much human beings are changing our planet's climate. There's an interesting thing that happened right here at the end. You'll notice we had a little dip. So if you look at the peak there, and the trough there, between 2010 and 2011, sea level actually went down just a little bit. Next slide. I think it's the next slide. Yes. So if you take out those wiggles, those ups and downs, the yearly back and forth between oceans and land, you get a clearer picture of this rising ocean, the rising oceans. And you can see right at the end we had a dip. And it turns out, this is really interesting, the dip was caused by an exchange of water, again, between the oceans and the land. And if you look in some other observations, you can actually tell where this water went. And the reason for the change was because of something in the Pacific Ocean we call El Nino, and the cycle between El Nino and La Nina. And this is a massive phenomenon that happens in the Pacific Ocean. Sometimes the Central Pacific warms up, and sometimes it cools off. And whenever it does, it shifts the rainfall patterns around. And if you go to the next slide, we can actually see that in some places, they got massive amounts of extra water, extra rainfall. And it was so big in Brazil and in Australia. You might remember a year or two ago, last year, there were massive floods in northern Australia. The result was such that this water actually lowered sea level. Enough rain fell that sea level actually went down. So it's kind of amazing to think of. But if you look where it landed, actually it landed in the tropics, right? It's warm here, and it's warm there. So it didn't fall on some glaciers or ice sheets where it might live for a long time. It fell in the tropics, and there's a massive river here, and this water is going to run back off into the oceans. So this is a temporary reprieve from global sea level rise. We're not looking at a long-term downward trend. In fact, if you look at places like Antarctica and Greenland, they're actually losing mass. They're losing ice. And you can still see that even now. Okay, so it's not just the oceans that are changing. Of course, the ice at the top of the planet is changing. This is a picture of the minimum in sea ice, the summer sea ice. In 1979, the first year we have satellite data. And if you click the next one, this is the year 2008. So if you just go back and forth a couple of times, you can see that the extent has been massively reduced over the last 30 years. And I didn't just pick these to make it look that way. If you click the next button, then you can see that there's a downward trend over the last 30 years. In fact, the worst year was 2007. In this year, the sea ice not only retreated, it pulled away from it pulled away from the North American continent and left a huge gap in ice right there. And there's a very top-level predator that lives in Northern America, the polar bear, and it uses this ice to actually hunt. They hunt for seals, and the ice was so far retreated that there were reports of polar bears swimming 60 miles and polar bears drowning because they couldn't find an ice floe big enough to hold them and hunt for seals. Now, I'm not a biologist like many of you, but my understanding is that these critters are scavengers, and so global warming may not spell the end of the polar bear. They could always go south and eat some Canadians or something. But it does remind us that climate change is happening in a way that these top-level predators are beginning to feel it. They're beginning to experience the impacts of global warming and climate change. And you might imagine that there's another top-level predator that will soon begin to feel these effects as well. Okay, so next slide. We have the sea ice. We also have the Greenland ice sheet. So when this water melts, or when this ice melts, this ice is floating, just like the ice in these pictures. And when it melts, it does not cause sea level rise, because it was already floating. But the ice here is on land. And if it melts, or if it runs off quickly, it does cause sea level rise. And so in the next slide, you can just see this little animation. Yeah, if we'll just click once. The floating ice doesn't raise sea level. the land ice does. And also, if you push a glacier off more quickly, if calving occurs more quickly, it can also raise sea level. You have rivers of ice flowing into the ocean. Okay, so we actually have this really great satellite on the next slide called GRACE. And this is a really cool toy. It's actually a pair of satellites, and they chase each other around the planet. And whenever one goes over something heavy, just from the pull of gravity, it speeds up a little bit. And then when the second one follows, it catches up. And so by measuring the distance between these two, you can actually infer how heavy the thing is that you're flying over. It's a really neat trick. And in this case, if it's flying over the continent of Greenland, we can actually use these two satellites to weigh Greenland. And when we do, we find that Greenland has been on Jenny Craig. And it's lost about 1 trillion tons in the last 5 or 6 years. So Jenny Craig, go for it. Anyway, I need to update this. Actually, what's interesting is you can see the trend in this period, but if I were to add on the next few years, there's actually an acceleration as well. It seems that not only is Greenland losing mass, but it's losing mass at a faster and faster rate. And here you can see the 2007 year when we had really warm Arctic, and we also had a lot of melting in Greenland. Okay, so it's not just from space that you can see these things, of course. If you visit glaciers in Alaska, there's all this beautiful photography of glaciers in the 30s and 40s. And, if you go back today, you can see the retreat of this glacier. So all of this was once ice, and actually not so long ago. And it turns out that glaciers all over the world are retreating this way. Something like 90% of all the glaciers in the world are estimated to be in retreat. So this is definitely something that's happening around the entire planet. Next slide. One of my favorite pieces of evidence for global warming, though, actually happened a few years back. In late January of 2002, a NASA satellite took this picture of the Larsen B ice shelf. Now this is an ice shelf is basically a big blanket of ice that floats on the water. And it forms because these rivers of ice flow down off the mountains and into the water, and then they just float out and form this big sort of blanket. And what they saw were these little dark dots all over the surface of the ice shelf. And they figured out that these were little pools of water because the melt was such that it began to cover this part with water. And so eventually, a few months later, the satellite flew over again, and this entire shelf had broken off and been torn completely to pieces. So all this stuff in here is icebergs and just crushed pieces of ice from this entire ice shelf collapse. And it was something like the size of Rhode Island. Now, the interesting thing to me is not so much that the ice shelf collapsed. It turns out that a few years later, some scientists went in here somewhere where the ice shelf used to be, and they drilled a sediment core, and they found that this ice shelf was 10,000 years old, at least. So it went all the way through the Holocene, and it survived the medieval warm period and all these little ups and downs during our relatively stable climate. But it wasn't until the warming of today that it finally broke up. So this is a pretty massive change, and it's something that's only happened because of today's warming. So nothing in these cycles of the last 10,000 years could have caused it. Not even Hugh Hefner was this old when he broke up the last time. Okay, so I think if you're not seeing the evidence for global warming and climate change, then the only real explanation for that is that you're not looking for it, because it's really all around us. Now that doesn't mean that you can walk out in your backyard and stick a thermometer in the ground and say, I see global warming. You do have to look at larger data sets and longer time series and things like that. But really, the evidence that human beings are changing the planet's climate in a huge and fundamental way is all around. And to not see it is really to not look for it. So, what's my final message here, just to wrap this up? A lot of people ask me, so what are you going to do? What do you do about global warming and climate change? And, the typical answers are all true. You should try to conserve energy, you should change your light bulbs, you should drive a fuel-efficient car, etc., etc. And all those things are great. But what I think you have to realize is that those things are not going to be enough by themselves. We really have to get get together as a society, and we have to talk to our leaders. We have to vote. We have to tell our elected officials that we think this is a big problem and it should be a priority for them. So if you haven't written your congressman, or if you don't know who your congressman is, you should find out. You should do a little homework, and you should let them know. I've met a lot of congressmen and senators and things, and they really do pay attention if their constituents take the time to sit down and write them and tell them what they think. You have to remember, we live in a representative government, so we elect officials who go to represent us. And there's no way they can represent us if we don't tell them what we want. So I really think we kind of have a responsibility here. It's not just planting a tree or driving a Prius. We really do have to speak up about this. Okay. And I'm just going to say that I think that eventually, the story about Rush Limbaugh and our correction is sort of like the way that we will deal with this climate change problem in the end. Eventually, the truth is going to get us. We can deny it, we can mislead people and reject it and suppress it, but the weight of the truth will eventually win. And with that, I think on my last slide, I'll stop and see if you guys have questions. So who has a question? Who needs coffee? No? Okay. Yes?
How do you feel about carbon offsets?
Carbon offsets. So the idea behind a carbon offset is basically that you pay somebody to go plant a tree somewhere and it sucks carbon out of the atmosphere. That could be a great tool. It could be a great mechanism. But until we it can help. But at the end of the day, I think what really has to happen is that we have to find a new source of energy. We can't forever continue to dig up carbon out of the ground and burn it and put it in the atmosphere. We really do have to go back to the source. So things like offsets are great, but you do also have to know that they're really doing what you think they're doing. So we don't really, I think we probably don't yet have a system of checking on the offsets. So if you buy a carbon offset from somebody, where is that money and resource really going? Is it really going to reduce carbon? Is it just stopping somebody from cutting down a tree they were going to cut down anyway? Maybe it is. Maybe those things are good. But we don't. I think we're beginning to build those kinds of systems, but we need a lot of vigilance to make sure that they're really doing what we think they're doing. But in principle, it's a great idea. Will they work? We have to see. And I think they won't work entirely, but they could be part of the solution. There was another one over here. Yes?
What does your typical day at work look like?
My typical day at work? Well, usually I sit in front of a computer, like you, but I'm not on Facebook. I know you're on Facebook. But most of what I do is analysis of satellite data and things like that. But of course, there's all kinds of scientists. There's people who go to sea. There's people who actually think up the next round of satellites and things like that. But mainly I'm a computer jockey, and then I get to come talk to people like you too sometimes, which is a great part of my day. Other question? Yes.
I have a question, and I took Professor Craney's class on UTAR a few years ago, and I'm sorry to say I don't remember if we talked about this, but would you
There will be another quiz.
Okay. Good thing I took notes here. Would you be able to tell me, does it matter how CO2 enters the atmosphere, whether it is anthropogenic or whether it's from ice melting or bogs or cows? Is there a difference in how it acts, how it behaves?
I think I think it would be chemically. I think it would be a very subtle, small difference. I mean, maybe the CO2 from the bogs has a different isotopic ratio, and so those things make it be absorbed or whatever in different quantities in different places. So I think you might be able to trace it. I don't think it would have a big, I don't think it would have a big impact. Although, well, that's not entirely true because some of the carbon that comes from bogs and things is in the form, winds up being in the form of methane. And methane is it's actually a much more powerful greenhouse gas than CO2, but it has a much shorter lifetime in the atmosphere. Methane eventually breaks down into carbon dioxide in the atmosphere itself. And so the release of methane can cause a really short-term, quick warming, but it dies out more quickly. And so really it's the carbon dioxide in the end that is the biggest in terms of the physical climate. So I don't know if I answered your question, but I tried. Yes?
When it takes 1,000 years for the entire ocean to be affected, is that like a heat measurement or like an energy measurement of like 1 degree difference at the bottom of the ocean, or what is it specifically measuring?
That's exactly right. It's how long it takes the temperature signal to spread through the whole ocean. In a way, it's how long it takes the ocean to mix once completely. There's these really slow-moving things called the overturning circulations in the ocean. So that's the process where stuff at the surface slowly sinks and then it spreads out and then it slowly mixes back up. So if you put warmer water in one of these overturning regions, then slowly the warmer water will spread down into the deep water and eventually fill up that volume and eventually cause the entire ocean to be warmer than it was. That said, the water at the bottom is still going to be colder than the water at the top, like it is today. And so that process takes a long time. But yeah, it's basically a measure of how long it takes to, say, if I put something in the ocean right here, for it to spread out and kind of fill up the entire volume of the ocean. Does that make sense? Mm-hmm. Good questions. Yes?
I have 2 questions. The first one is whether the contribution to the ocean temperature of Earth's radiation or like underwater volcanoes. I mean, I have no idea how much heat the Earth is releasing from into the oceans. Is that a real amount?
Yeah, there is geothermal heating from the center of the Earth out through the crust and back out into space eventually. But it's very small compared to the energy that we get from the sun, the energy that we release back in the atmosphere. It's, I think, at least 100 times, maybe many hundreds of times smaller.
My other question is about your thoughts on science education, and not just K through 12, but really at all levels, graduate school, postdoc, and because what you have up here is really about scientific advocacy, engagement, and policy. And you know that there are plenty of scientists who don't think scientists should bother with that, or who don't think serious scientists are going to be the ones to bother with that. It's related to the kind of value-free notion of science, that we should just do the science and then it's for other people to figure out kind of implications, so forth. So how do you start? I think it's a scientific culture issue. How do you think that can begin to change? Right. What's an effective way of sending this message to people, graduate students and postdocs? This is part of being a scientist.
Right, right. That's a really great question, and it doesn't have a short answer. I think that the scientific community has been a little bit delusional to think that it is totally divorced from the policy or political realm. I mean, even at the most basic sense, the vast majority of scientific funding comes from the public, and so we at least owe them an explanation of what we're doing and some general sense that we're doing things that they want funded. I also think that it's a false choice between objective scientific work and a political stance. I think that if you look back in history, there are plenty of prominent scientists who have taken strong political stances and still been respected for their work as a scientist. I don't think that's impossible, and I don't think it's necessary. you know, I think people also realize, however, when you sort of misuse your integrity as a scientist for political purposes, or when you're hypocritical in your work. When you know, I think that the general public is pretty good at figuring out if you're doing the former, and the scientific community is pretty good at figuring out if you're doing the latter. I heard there was a great talk at AGU a couple of years ago by Michael Oppenheimer, and he said that he gave this example of Bill Frist. I don't know if you remember the senator from a few years ago. There was this case of the woman who had brain damage and was on life support for like 20 years. And there was a fight between the parents and the state about whether or not they could end her life support and let her end her life. And Bill Frist, suddenly this Senate leader, who was also an MD, made a strong pronouncement that he thought that her, without having seen her medical record, he said that, well, you know, there's surely, you know, she's probably not in a permanent vegetative state. I don't remember the language exactly. But the point was that he, as a politician, used his status as a medical doctor as well to try and make a claim about her medical condition when he really had no right to. And that kind of hypocrisy, some have argued, might have been part of the reason he lost his job as Senate Majority Leader. And so I think that the public has a pretty keen eye for when a scientist or a medical doctor or a professional is kind of speaking out of turn in terms of their job. And of course, the scientific community has a very sharp eye for whether or not your political leanings are leaking into your work. That's why we have a peer review system. That's why people continue to continually redo each other's work and scrutinize it for accuracy. So I think we have systems in place to avoid the kind of problems that scientists have fixated on and sort of created this world for themselves that they have to live only in the science realm. So that was the short answer. Yes.
Josh, would you comment on, you touched on methane. There's another powerful greenhouse gas, water vapor. And the connection is the following. Okay, so we've got a lot more cows. We had chickens back then. We've got a lot more cows on this planet, right? And those cows are a major source of methane, short term, right? And we've got a tremendous transformation of the landscape of the earth to grow food for 9 billion people. And so that desertification is taking place on a massive scale. What's the relative importance of water vapor and methane linked to human activity? Your original picture of Al Gore saying people do it, right?
Right.
What is the relative importance of those things relative to CO2? I mean, CO2 is obviously contributing, but what about these other parts of the equation?
The best estimates are that CO2 is the biggest contributor to climate change. But methane is not unimportant. It's I don't know the exact number. It's less than, I think it's less than half of it's obviously less than half of the forcing, the change that we're applying to the climate. But I want to say it's 20% or something. I don't know exactly the number. So methane is definitely part of it. But again, the methane is in some ways a smaller concern because its lifetime in the atmosphere is so short. Water vapor is really a different beast entirely because you have to ask for each one of these constituents. Water vapor, by the way, is a greenhouse gas. It's a very powerful greenhouse gas. But each one of these constituents of the atmosphere, each one of these things that's in the atmosphere, you have to ask what is its source. And the source for water vapor in the atmosphere is the oceans. Remember, 2/3 of the planet are covered with oceans, right? So what sets the amount of water vapor you have in the atmosphere? It's actually not what we're doing or the water vapor that comes out of your tailpipe if you drive a hydrogen vehicle or something. What sets the amount of water vapor in the atmosphere is actually the temperature of the atmosphere. So however much water vapor the atmosphere can hold, it will take out of the ocean. Because it has basically an infinite source. From the atmosphere's point, it's an infinite source of water. So it will just equilibrate its water content based on what temperature it is. So water vapor is not actually a forcing, it's what climate scientists call a feedback. Because if you warm the atmosphere, it absorbs a little bit more water vapor, and that warms the atmosphere a little bit more. But it's not a runaway warming, and that has to do with the details of just how much water vapor is taken up and how powerful it is and so forth. So it's not a runaway problem, but it basically gives you more bang for your CO2 buck. That's basically, it's like a frequent flyer mile or something of climate change. So water vapor is not really it's a greenhouse gas, but climate scientists don't consider it a climate forcing, something that's driving the climate. It's really reacting to what's already happening.
Can you link that back to both changes in agricultural practices and the massive degree of urbanization that's putting all this concrete that absorbs energy and makes heat islands and stuff like that? Can that be linked together in any coherent fashion?
Yeah, I mean, of course, the change in the changing of the surface of the Earth, the reshaping of the surface of the Earth, is a significant part of climate change. It's part of the reason we're producing methane, which is contributing. It is all it is part of it, but I don't have the specific breakdown of how much is which part. I could get back to you on it. But it's there. It's important. You know, the urban heat island effect is really important in Los Angeles. For example, in Los Angeles, it's warmed up 5 degrees Fahrenheit in the last 100 years. Of that 5 degrees, probably 3 are heat island, just because we're turning this sort of scrubby chaparral into concrete parking lots and so forth. But the heat island effect in some places like Tokyo is 13 degrees. And in, I think Mexico City is another one. It's enormous. It can be an enormous effect. So those things are happening too. They're not part of the global picture, they're local, but if you live there, it still matters. Absolutely. Yes?
In terms of carbon absorption into the ocean, it turns into, like, how does that drive that? So how does that change things?
The carbon being, of course, if the ocean wasn't there and it wasn't absorbing the carbon, it would more of it would stay in the atmosphere. Almost all of it would stay in the atmosphere. So you would have quicker greenhouse effect. You would have stronger forcing.
But I'm thinking, like, how does it affect, like, say, like currents or like what's happening in the ocean?
But how does it affect? Right? How does it affect the oceans? The carbon doesn't affect the current too much because the currents are really set by the winds and how salty it is or how warm it is. But what it really affects is the ecosystems, because at the very base of the ecosystems are all these little critters that need calcium to build skeletons and things. And as you add carbon dioxide to the ocean, it gets more acidic, and that makes it more difficult for the little critters to build skeletons. And of course, those plankton and so forth are all at the bottom of the food chain, and so they can have an impact that goes to the entire food chain. So ocean acidification is one of the potential looming disasters. It's something that we're just beginning to understand, but it's a little scary because it could have really big implications. I don't think we really know how the ecosystems are going to react to the change in the acidity that's on the way, but that's a really big deal. A huge fraction of the population of the Earth depends on seafood as its primary source of protein. So those, it could be a big deal. Yes.
This third Jason's satellite is called, right? Is that different than how is it different than?
It's exactly the same. In fact, there are battles at JPL over how different it should be or whether it should be different, but it's basically exactly the same. And that's kind of good and bad. I mean, the measurements gotten more accurate over time. Each time they build one, they make it a little bit better and It's no less noisy and newer parts and stuff like that. But really, the fundamental measurement is almost exactly the same, and the scientists really like it that way, because then there's no question about whether or not what you're seeing is global climate change or just the fact that you switched yardsticks halfway through, right? So actually, in fact, I didn't show it in that plot with the global sea level rise, but each time we've switched from like TOPEX to JSON 1, from JSON 1 to JSON 2, and hopefully from JSON 2 to JSON 3, there's actually overlap. There's about 6 months, or in some cases a year, where the two satellites fly just about a minute apart, one behind the other, and they measure the same ocean through the same atmosphere and the same conditions, and they're calibrated across the two missions. And it's only because we have that kind of cross-calibration period that we can build this record where you can see global sea level rise for 20 years. So we're actually fighting right now because JSON 3 is facing funding shortfalls, right, your congressman, and so we're trying to make sure that we have enough money to get it launched before JSON 2 dies. Now, these satellites have a pretty good record of lasting a long time, well past their design life, but still, you don't really want to have the potential for a gap, because it throws open the question, well, hey, maybe sea level went down between those years and we didn't notice. Right? So it's a big deal. Yes?
Well, I read about places like Maldives being very concerned about sea level rise. I'm wondering, on the scale you talked about, if we're being just at the level now, in the next 100 years, are we talking about losing countries or cities?
Absolutely. There's lots of countries in the Indian Ocean and the Pacific Ocean that have, almost all their entire country is 3 feet above sea level or something like that. And 3 feet in the next 100 years, if the rate stayed the same, 3 millimeters per year, if it stayed the same for the next 100 years, we'd still get 1 foot in 100 years. So 1 foot's actually the lowest any sane person would claim for sea level rise in the next 100 years. And the highest anyone would claim is probably about 6 feet. And 3 feet is sort of a best guess. But 3 feet is definitely going to wipe out a bunch of islands in the Pacific. Pretty big areas in our own, a lot of the San Francisco Bay Delta is 3 feet reclaimed, 3 feet above current day sea level. Of course, Florida, the whole East Coast, the Gulf Coast, all these places are really, really susceptible. Some, in addition to that, some places like Louisiana are sinking also. So they're getting a double whammy. But absolutely, we're definitely going to see in the next 100 years people displaced by sea level rise. We're going to see places that have to be protected. There's 2 things you can do in the face of sea level rise. You can adapt and you can retreat. So you can either build a wall or you can tear down a building. That's the only responses. And which one you should do depends on how fast sea level is rising and a whole bunch of other things. But we really need to know in order to make that kind of decision. So, great question. Yes?
So we've already seen like a decrease in the pH of the ocean. And I was wondering if we completely stopped emitting carbon dioxide, like methane and stuff,
Right.
is that effect reversible?
That's a really good question. I think it's really hard to reverse it because you have to draw down carbon. Basically, the ocean and the atmosphere find some equilibrium over time, and we've raised the concentration in the atmosphere, and so they're trying to reach equilibrium, and the ocean will absorb some more out of the atmosphere. And so if you turned off the faucet of CO2 today, the ocean would still take up some amount of carbon. So I think they would actually still continue to get more acidic for a while. And then they would probably level off. And on the very long time scales, there are other mechanisms for taking it out of the climate, but it's going to be there for a long time. The other things in the ocean happen too. Eventually, over a very long time, like I said, you mix that water, and so you might be able to get water from down deep that had, most of the carbon starts out in the surface layers, and so as you mix it down, you can dilute the carbon. And you know, most of the critters live near the surface, so you might be able to dilute their environment a certain amount. But getting it back out is actually really hard. It's way easier to just not put it in the first place. Other questions? Yes?
Has there been any research looking at maybe a correlation between how absorbent the ocean is, whether it be light or whatever chemical, and the amount of plastic particles that are in the ocean?
That's a really great question. I don't know. That's a great one. A number of people are starting to study plastic in the ocean. There's a huge amount of plastic in the ocean. You know, you've probably heard of the Great Pacific Garbage Patch. And actually my office mate in graduate school recently published the first paper about the Great Atlantic Garbage Patch. There's one of the Atlantic Oceans too. And so, yeah, there's all this plastic there. It's arranged, it breaks down into little pellets. But I don't know about, in terms of absorption of energy or CO2. I know it's bad for the fish.
Because I just know that there's so much of it, so many,
Right.
like for instance in the Pacific Gyre, there's so many microscopic pieces for every 2 liters of ocean that you pick up out of.
That is a great question. I think you should do a project on that and tell me the answer. You can write a science paper on
There's
it.
another garbage patch is on the news tonight, which is the tsunami garbage patch.
Oh,
They
yes.
said it's like 180,000 tons of debris that just got washed out and is headed across the Pacific.
Right, right. There's a massive current that leaves the coast of Japan called the Kuroshio and the Kuroshio extension. And it makes up the northern part of the Pacific Gyre. Basically, it shoots right across the ocean to California. So yes, it will be here eventually, probably in a year or two, something like that. And you can pick up Japanese housewares off the beach. Right. Contrast to glass bottles. Other questions? Well, thank you guys. That was